Here's sort of a classic thermodynamics problem that is actually more maths than physics or thermodynamics, although it uses a few elements which are related to the ideal gas law especially. And if you're doing thermodynamics as a first year engineering student, or if you're doing it as part of your high school syllabus, and if there are any questions you want to see me do on this channel, let me know in the comments. So let's read the question and then let's see how we can approach it. The question states that we're dealing with two processes. So we've got part A and part B, and we have to find the maximum attainable temperature of an ideal gas in each of those processes. Okay, so the first process, part A, all we know is that the pressure as a function of volume, so I'm writing it like this just to show that it depends only on volume in this case, that's equal to P naught minus alpha V squared. And the question says that P naught, alpha, and then beta, beta will appear in part B. So those three are positive constants, and V is the volume of 1 mole of gas. So what this means is when we write the ideal gas law, which is PV equals nRT, the V that we're actually dealing with implies that on the right hand side our n, our number of moles, is equal to 1. So the V in this question satisfies PV equals 1 RT, or just RT. Okay, so this is the form of the ideal gas law that we're going to use for A and B for this whole question. Right, so then let's try to understand why there is a maximum temperature to begin with, and then we'll try to find uh, when that maximum temperature occurs, and we'll also find what that maximum temperature actually is. So what I would do here is I would take this pressure and I would just put it in the ideal gas law. So if I do that, I will get that the pressure, so instead of P, I'm just going to write P naught minus alpha V squared multiplied by V is equal to RT. So that instantly gives us an expression for temperature as a function of volume. So we've got T as a function of volume is P naught minus alpha V squared, and then times V over R. And you can actually see that this is just a function of volume, because everything else on the right hand side, P naught, alpha, and R, they're all constants. So let's maybe try to rewrite this in a slightly different way. So this is going to be P naught times V minus alpha V cubed, everything divided by R. Okay, so the question is asking us to find the maximum attainable temperature, and hopefully you all know by now that to find the maximum temperature we have to differentiate this. So if we differentiate the temperature with respect to the only variable, which is volume, then we'll get P naught minus 3 alpha V squared over R, and if we make this equal to 0, we're going to find the stationary points. So let's see what we get. So if this is equal to 0, it means the numerator has to be equal to 0. So that's P naught minus 3 alpha V squared is equal to 0, or V squared is equal to P naught over 3 alpha, or V is equal to square root of P naught over 3 alpha. Okay, so this tells us that when the volume is equal to this, we have a stationary point. We don't yet know whether this is a maximum, minimum, or maybe even an inflection point, but we have to show that this is actually a maximum, or this corresponds to a maximum. So the way to do that, obviously we have to find the second derivative. So if we differentiate this again, we get, so P0 is a constant that gets cancelled out, and then minus 6 alpha V over R. And as you can tell, alpha and R, they're both positive. V is a volume, so that's clearly positive, and the minus here makes the whole thing negative. So this is a concave function, basically. That's what this tells us. And if it's a concave function, then it will have a maximum. So V corresponds to a maximum according to calculus theory in maths. So we found the location of the maximum. Now we have to find what that maximum temperature is. So let's go back to the actual expression for the temperature as a function of volume, which is this. So that's P naught V minus alpha V cubed over R, and Tmax is going to be simply P naught times, and instead of the volume V, I'm just going to use the location of the maximum to find the maximum temperature. So that's P naught over 3 alpha minus alpha times V cubed. So V cubed is going to be P naught over 3 alpha times square root of P naught over 3 alpha. And everything is over R. I'm going to remove this dot. Actually, no, this is P0. Okay, so let's see what we can do here. So we can cancel out this alpha and this alpha. And then we have P naught over R square root of P naught over 3 alpha minus, and then we have P naught over 3R. So I'm just splitting up the fraction into fractions. Square root of P naught over 3 alpha, and that is 2 P naught over 3R square root of P naught over 3 alpha. And that's it. That's the, well, let's call it, let's put some units here. Let's say this is in Kelvin. So this is the maximum temperature. Obviously, it doesn't have a value because the problem doesn't give us values for P naught alpha, and I think that's it. And we know what R is, but whatever P naught and alpha are, if you know the values, you can put them in here, and whatever comes out will be the value of the maximum temperature, and that is part A. Okay, now let's go to part B, which is pretty similar. So in part B, we have a different process. So we still have pressure as a function of volume, which is equal to P naught, and then we have an exponential. So e to the minus beta times the volume, where V is the volume of 1 mole of gas, which means this is the form of the ideal gas law that we have to use. Okay, beta is a positive constant as well as P naught, right? So let me make a note of that here. We know that beta is positive. So what we can do then is the same thing as before. I'm going to write PV is equal to RT. So P naught e to the minus beta times V, that's the pressure. So I'm just replacing this with this because they're equal, and then times V is equal to RT. So we can move things around and just make T the subject. So T as a function of volume is going to be P naught over R. I'm writing P naught over R in front because that's basically a constant. Yeah, it's just a number. E to the minus beta V times V. And like before, we're going to differentiate this to find the maximum, the location of the maximum. So we say the first derivative with respect to V has to be equal to 0 to find the stationary points. And then we have P naught over R comes out in front of the derivative because it's a constant. And then we have to apply the product rule. Okay, because this is a product, it's a function, it's an exponential times a first degree, first order polynomial, basically. So this is going to be, let's see, minus beta e to the minus beta v, that's the derivative of the exponential times v, and then plus e to the minus beta v times 1, basically. So that is equal to 0. Okay, let's take it with us to the next page. And let's factorize e to the minus beta v. And in the bracket, I'm going to have minus beta v plus 1, and that is equal to 0. So the only way in which this is 0, this is a product of three things. So the only way in which this is 0 is if this is 0, which cannot be true, because P naught is non-zero. This should be 0, which again is not true. Exponentials are never equal to 0. So the only way in which this makes sense is if the bracket is equal to 0. So we have minus beta times v plus 1 is equal to 0, which means that v is 1 over beta. So v is equal to 1 over beta is a stationary point, and technically you have to check whether this is actually maximum or minimum. Okay, and to do that you have to take the second derivative, but I'm not going to do that here. So you can try this on your own and you will actually confirm that yes, this corresponds to a maximum. So what I'll do instead is I'll just find the maximum pressure. So let's write T as a function of volume again. So that is P naught over R e to the minus beta V times V. And the maximum temperature is going to be P naught over R times e to the minus beta times, and instead of V, I'm going to write the V that corresponds to the maximum, which is 1 over beta, and then times 1 over beta, like this. So that's P naught over R e to the minus 1, 1 over beta. So T max will be equal to P naught, and then you've got beta times E times R. And if you know what the constants are, well, you already know what R is, and you know what E is as well. So if you know P naught and beta, you can actually find what the maximum temperature is for this second process in part B. And that's the end of the question.